Okay, let's get started. Good morning. Okay, so today we're going to be looking at section 4.4. We'll look at indeterminate forms. And this very useful technique called L'Hopital's rule. Okay, so as a reminder, remember we used to do limit problems where we end up getting things like 0 over 0. So a very simple example to remind you of the kind of thing we did before. Suppose we have x squared plus x minus 6 over x squared minus 4, and we're looking for what happens to that function as x goes to 2. Notice that if we let x become 2, then the numerator becomes closer and closer to 0. So does the denominator. 2 squared minus 4, there's our 0. And this is one of the many indeterminate forms. And the way we used to handle this was we look for things that could be factored and then canceled, and then find the limit. So the old way of doing things, remember, we factor the top, and the bottom. We discover what was causing the 0 over 0, and then we got rid of them. And in the end, we let x be 2, and we get 5 over 4. Okay, so this was fine when we had polynomials, and when we have things like trig, things get a little bit more. Oh, it's going to be a fun day with the mic again. Okay, I think it's good for now. Okay, so that was the old way of handling things. We look for things that factor, and occasionally things got complicated. We had to do rationalization and all sorts of special things. L'Hopital's rule is a way to handle stuff like that. It allows us to find the limits of functions that approach zero over 0 or infinity over infinity. Stop. Okay, so this S right here, in this word L'Hopital, it's a French name. This S is silent. Okay, just pretend that S is not there in L'Hopital. It looks like hospital, and it has roots in the same word we use to talk about hospitals, but for this here, this was the guy's name. Actually, his title. He was a French nobleman, mathematician, did a bunch of things. If we have time, I'll tell you a little bit about this guy at the end. Okay, so this rule says that if we're looking for the limit as x approaches a of f of x over g of x, And suppose that the limit of both of them, f or g, or if they both go to 0 or both go to infinity, and that's how you get 0 over 0 or infinity over infinity. 0 over 0, we have an example here, and we've seen infinity over infinity before. Then the rule says that the limit of this expression f over g, if you do nothing to it, it goes to 0 over 0 or infinity over infinity. But the rule says that we will get the same limit if we take the limit of the derivatives of both f and g. So f prime on the top, g prime on the bottom. This will give us exactly the same limit if these two conditions, either of these two conditions are met. Both go to 0 or both go to infinity. Stop. It's not that. It's usually not doing that. If I don't move, I think it does pretty well. Ah! And it's not my shirt. It doesn't normally do that. Okay, so. Okay, let's try this on the thing we did at the beginning. Okay, so the old way we factor and cancel stuff and we got a limit. Now let's try L'Hopital's rule. Now in class, whenever I use L'Hopital's rule, I'm going to put a little h on top of the equal sign. That just means that going from here to here, I apply L'Hopital's rule. The book does the same thing, and I think it's good to show what happened there. So that h means we apply the rule. The rule says that because this is going to 0 over 0, we're going to take the limit of the derivative of each of these. Derivative of the top is 2x plus 1. Derivative of downstairs is 2x. Okay, and now notice what happens when I put in x is equal to 2. I get 5 to 4 plus 1 over 2 times 2. So it's the same limit that we had gotten using the old canceling and factoring way. Okay? Okay, let's do a few more examples. Let's look at this one. Limit x goes to 0 of x plus sine of 2x over x minus sine of 2x. Before we get all excited and apply L'Hopital's rule, we have to always make sure the limit appears to go to 0 over 0 or infinity over infinity. So we must check if this goes to one of these two things before we can use L'Hopital's rule. L apostrophe, the word hospital. Okay? If it doesn't, then we are not allowed to use L'Hopital's rule. If you don't see one of these two, do not apply the rule. You will get the wrong answer. So let's see. If I put in a 0 here, I get 0 plus sign of 0. That's a 0. And here I get 0 minus 0. So that's okay. Now you've made sure that it goes to the right form. We can use L'Hopital's rule. So again, my little h above the equal sign means I apply the rule here. We'll take the derivative of the top, 1 plus cosine of 2x times 2. Remember to use chain rule as usual. Downstairs, same thing. 1 minus cosine of 2x. Again, chain rule applies. We get a 2. Now we try to see what happens when we put in x is equal to 0. X becomes 0, goes into here. Cosine of 0 is a 1, right? So 1 plus 2 gives me a 3. Downstairs is 1 minus a 2, negative 1. So in the end, the limit I get would be negative 3. Okay, does that make sense? More examples. Let's change one of these to a cosine. As usual, always check if you get 0 over 0 or infinity over infinity. These are the only two forms you are allowed to use that rule on. So let's see. When x becomes 0, I get 0 plus 0. I get 0 on the top. When x becomes 0, I get 0 minus 1. Okay? So this is not 0 over 0 or infinity over infinity. Do not use L'Hopital's rule. In general, the answer will be wrong. There may be situations where you use it incorrectly and still get the right answer, but that's purely coincidence. That's just a fluke. It is not the right answer in general. So notice what happens if I simply plug in 0. I get 0 on the top, and I get minus 1 downstairs. 0 over anything that's not a 0 is a 0. So that's just simply a 0 as the limit. If you use L'Hopital's rule, you will not get the right answer. You will get a wrong answer in general. Any question? All right, let's look at a couple of cases of infinity over infinity. Here we're looking for the limit of natural log of x over the square root of x as x approaches infinity. So let's see. When natural log of x, when x becomes very large, natural log of x becomes large too. It slowly increases, but it goes to infinity nonetheless. And of course, the bigger you make x is, the bigger square root of x is also going to be. Right? So we get our infinity over infinity. Remember, what this really means is that we have a big number over another big number. The limit could be anything depending on how big the numerator is compared to the denominator. Right? Remember, if we had a polynomial once, if the numerator had higher power, then the number on the top is bigger. So that went to infinity. If the denominator had higher power, then it went to 0, that kind of thing. Here, we don't have polynomials, but the same idea is still here. It's a big number over a big number. We don't know which one is bigger, and therefore, that alone doesn't tell us what the limit is. So because we see an infinity over infinity, we are allowed to use L'Hopital's rule. And what L'Hopital's rule is saying is now, instead of looking at how these things behave, let's look at how fast they go to infinity. If the numerator goes to infinity faster than the denominator, then this thing's going to get very big. If the converse is true, it goes to 0. So let's see. Take the derivative of top and bottom. Natural log of x has a derivative that's 1 over x. Downstairs, that's x to the 1/2. So we get 1/2 x to the negative 1/2. Let's simplify this a little bit. This is 1 over x over 1 over 2 radical x. We don't like complex fractions, but we know this is equivalent to 1 over x times the reciprocal of what's downstairs. Which then becomes 2 radical x over x. Continue simplifying. I can cancel a radical x with one of these x's here, and that gives me a radical x downstairs. All right, and now at the end of the day, I end up getting this thing right here. And this thing would have the same limit as that, because we use the rule. The rule guaranteed that by comparing the rates instead of how individually they approach the big number. Now, when x goes to a large number, this becomes very large. So that ends up being 2 over a super large number, and that, of course, means the limit of 0. A limit of 0 in this context means that radical x is growing faster than natural log of x. So by comparing the rates, because this thing is growing so much faster, it's always going to be much bigger than ln of x. So this means radical x grows faster than ln of x. Even though they both go to infinity, the denominator is going to infinity much, much faster than the numerator. Therefore, the denominator is always going to be bigger than the numerator by quite a bit. And in the end, we always end up getting a small number. Any question on this example? All right, let's look at other examples. Sometimes you have to use L'Hopital's rule multiple times. Here we have e to the 7x minus 7x over x squared. And we want x to go to, sorry, missed something here, minus 1. Okay, e to the 7x minus 7x minus 1 over x squared. Again, check we have the right form before you do anything. If I let x be 0, this is e to the 0, that's a 1. That's obviously a 0 minus 1 over 0. So this goes to 0 over 0. That means L'Hopital's rule is okay. Is applicable. If not, and you insist on using that, you will get the wrong answer. You've got to make sure you have that or infinity over infinity. Okay, let's see what happens. Now we apply the rule, little h denoting that's what we did. We take the derivative up and down. This guy will give me 7 e to the 7x minus 7. Downstairs is 2x. Now, first thing you always want to do is to try to simplify. Look at the last example. We did a bunch of algebra to simplify and finally got something meaningful out of it. Here we don't have the same option. There's really nothing here we can do. There's nothing to factor or cancel or anything to do. But here, notice that when x goes to 0, this goes to 0 over 0 again. Right? This is 7 minus 7 over 0. And therefore, we're going to use L'Hopital's rule one more time. Okay, so now look at this thing here. I apply the rule one more time. That's going to give me a 49 e to the 7x. That disappears. Downstairs is a 2. Now this clearly doesn't go to 0 over 0 or infinity over infinity, so no more L'Hopital's rule. We stop right here. Whatever comes out of this is the limit that we get. So let's see, we get 49 times 1 over 2, and there it is, 49 over 2. Okay? Does that make sense? Any question on that? Okay, good. Now we're going to look at other kinds of indeterminate forms that are not 0 over 0 or infinity over infinity. But there's always something we can do to make L'Hopital's rule work for those cases. Let's look at this one. Limit as x goes to 0 of 1 over x minus 1 over e to the x minus 1. Okay, now see what happens when x goes to 0. When x becomes a small number, this becomes a very, very large number. So that's an infinity. When x becomes a small number, e to the small number is roughly 1. So that's also a 1 over a small number. This is also an indeterminate form. The difference between two infinity really means a big number minus a big number. Now we don't know which one is bigger. The first one could be 100 trillion, the second one could be a million. In that case, it goes to infinity. It could be 2 trillion minus 1 trillion. And in that case, the difference is 1 trillion. So we don't know which one is bigger. And the end result, just by looking at that, is not something we can tell. We don't know what it will really turn into without doing more to it. So the end, just by looking at it right now, we can't say anything about what it's going to do. This is not something we can use L'Hopital's rule directly. What we have to do is to somehow change this into 0 over 0 or infinity over infinity. If we can do that, then we apply the rule just like we've been doing on the last few examples. If you're looking for a fraction and you got two things here, the obvious thing to do is to find a common denominator and then combine them. So we can write the first one as e to the x minus 1 over x times e to the x minus 1. The second one is then x times e to the x minus 1 downstairs, and then an x on the top. And now we can combine these two things into one quantity, and if that quantity goes to one of these two things, we apply the rule. Okay, now let's see what happens. When x goes to 0, that's a 1. 1 minus 1 is 0. Minus a 0 is a 0. Downstairs is 0 times something. That's a 0. Okay, now it's the same thing. We haven't changed the function at all. We haven't changed the expression in any way other than rewriting it. Now it goes to the right form that we can use the rule on. Now we use L'Hopital's rule. Before I do that, let me rewrite the numerator this way. I haven't done anything as far as derivative goes yet. I will always put a little h on top of the equal sign when I do that. Okay, now we take the derivative. Upstairs, that's an e to the x minus 1. Downstairs, be careful with this part right here. When you take the derivative of downstairs, x e to the x is a part that you have to use product rule on. It's a product of two things containing x. Okay, so you get first times the derivative of the second, e to the x, plus the second, e to the x, times derivative of the first, 1, minus a 1. That's after the first time we apply L'Hopital's rule. Look for ways to simplify that, and there isn't any here. No cancellation can happen, nothing to factor. And let's see what happens. When x goes to 0, that's a 1. 1 minus 1 is a 0. Downstairs is 0 plus 1 minus 1. That's a 0 over 0. So we use L'Hopital's rule one more time. And once again, this part right here also is the same thing, right? So when you differentiate the second time, that is another product rule going on. Okay, so you may encounter these things like this once in a while when things get kind of involved. Just got to be careful in keeping track of stuff. So we apply one more time. Derivative of the top is e to the x. Downstairs, x e to the x, product rule, gives me that as a derivative. And then I have another e to the x that has e to the x as a derivative. Okay? Now let's see what happens when x goes to 0. That's a 1. That's a 0. That's a 1. That's a 1. So in the end, we get 1 over 1 plus 1. We get 1 over 2. And so what this is saying is that those two big numbers that are being subtracted from each other, doesn't matter how big they get, the difference between them will always hover around 1/2, no matter how big they get. The bigger they get, the closer the difference will be 1/2. So even though you got two gigantic numbers being subtracted, the difference is really, really small. Just 1/2. And that's the kind of thing that we couldn't determine without using L'Hopital's rule, unless we either graph them or make a table of values out of them. Question on this one? All right, more examples. Here's another different kind of indeterminate form. X goes to 0 of cosecant of 4x times sine of 4x. Sine of 1x, sorry. What's the cosecant of 0? What do you get? Cosecant is 1 over sine, right? So cosecant of 0 gives you 1 over a small number, infinity, right? So this guy goes to infinity. This guy goes to 0. This does not mean literally a 0. This means a small number. So what this really means is a big number times a small number. And once again, depending on how big the big number is and how small the small number is, the product could be anything. It could be 0, it could be 2, it could be 3, it could be infinity. It all depends on how big is and how small is. L'Hopital's rule allows us to compare the rates of how they become big and small. And the rates will tell us ultimately what happens. Still, just like the last example, we cannot use the rule right away. We have to turn this into 0 over 0 or infinity over infinity. If we see one of these two things, then we are good. We use the rule and we get a limit. And this seems pretty obvious. We just talked about cosecant being 1 over sine. So without doing anything special, we get sine of x over sine of 4x. As x goes to 0, numerator approaches 0, so does the denominator. All right, so we got one of these two forms. It's the good form that we want to see. By the way, sometimes you see this L'Hopital spelled differently. You see this funny looking accent mark on top of the O, and then the S disappears. So this funny looking accent mark, that's the more modern French spelling of the same name. In L'Hopital's own time, he would have written this way with an S here, even though the S is silent. And in modern French, that accent here indicates a missing letter that used to be there, but is silent and got dropped. So anyway, you may see that written that way sometimes. All right, so we got the right form. We take the derivative, apply the rule. Upstairs derivative is cosine, of course. Downstairs derivative is 4 cosine of 4x. Okay, now when x goes to 0, that's a 1. That's a 1, right? 4 times 1. So we get our limit of 1/4. Okay, so that's a very interesting thing here. We got a big number times a small number, but somehow, no matter how big and small they got, the product turns out to be 1/4 the whole time. It's a very interesting behavior that's not expected just by looking at them the way they started. Questions on this one? Yeah. It can be negative infinity because then it's just negative of infinity over infinity. It's the infinity over infinity that matters. What sign they carry doesn't really matter. Good point there. And by the way, that H is silent. But anyway. So any question on this example? All right, so let me talk about one last type of indeterminate form. We've looked at quite a few now. The last type we'll look at, these are collectively called indeterminate forms involving, they all have powers involved. So if you ever see 1 to the infinity, 1 to the infinity, 0 to the infinity, or infinity to the 0, these three are all indeterminate forms. That 1 doesn't really mean literally a 1. It means something close to 1. Those zeros don't literally mean 0. They mean something close to 0. So the last one here, for example, is a large number raised to a small power. Just like before, depending on how large is and how small is, that limit could go anywhere. So here's an example. Limit x goes to 1 of x to the power of 1 over x minus 1. See what happens when x becomes close to 1. That's close to 1. That's close to 1 over a small number. So that's infinity. So this means that a number that's close to 1 raised to a big power. Depending on how close it is to 1 and how big that big is, the final result is anyone's guess. And just like before, somehow change to 0 over 0 or infinity over infinity. This is a little bit trickier because we got a power involved. We really don't like that power being up there. But we know that if you don't want a power up there, you can just take the log of something and bring that power out, right? So here's how we handle this kind of thing. Let's call that thing whose limit we're trying to find, we'll call that y. So what we really want here is that thing y here. Let's find the limit of y. But we want to yank that power out of it. So let's take the natural log. If I take the natural log on the left, I take the natural log on the right. Left, there's nothing going on. But on the right, now we're allowed to move that power out to the front. So after taking the log, notice that we end up getting ln of x over x minus 1. And now notice that as x goes to 1, this thing here goes to 0 over 0. That means we can use L'Hopital's rule, right? If we see one of these two here, we can use L'Hopital's rule. So what we're doing here is taking the limit of the natural log of the thing we wanted. Once we find the limit, we undo that natural log by doing exponentiation. Okay, so we apply the rule here. Upstairs is a 1 over x. Downstairs is a 1, of course. Sorry? No, derivative of x is 1. Yeah, so this goes to 1, right? This does not mean that the limit of that is 1. It means that the limit of the natural log of this thing is 1. So what this really means is that, right? The thing we wanted, whose natural log has a limit of 1. And the only way that can happen is if this thing approaches e. So the limit of x goes to 1 of what we really want is e to the first. You use exponentiation to undo natural log. So in the end, we end up getting e as our limit. And so you can look at that as another way we can define the number e. Question on that. Anytime you got something to do with power and things go to infinity, and one of those three forms, you handle them exactly the same way by taking the natural log. Okay? All right, so a little bit of history lesson here. I think this is very important that we know who is L'Hopital and where the rule came from. So this guy here, the rule that we call L'Hopital's rule actually was discovered by this guy named Johann Bernoulli. He was a family of very famous mathematicians and physicists. Bernoulli was hired by Guillaume de L'Hopital, the guy with L'Hopital, to tutor him in mathematics. L'Hopital was a fine mathematician, but Bernoulli was better, so he hired him to tutor. Part of the agreement there was that L'Hopital was allowed to use Bernoulli's discoveries as his own. So what he did is he published a bunch of stuff in his book. The first calculus textbook that we know in history was published by L'Hopital. Not James Stewart, no way. It was L'Hopital. Okay? So, but the book was full of Bernoulli's results, including the rule that we've been using called L'Hopital's rule. So a little segment from L'Hopital's book. Left is French, blah, blah, blah. What it really said here is just what we have been looking at. Notice we're looking for the denominator, numerator, denominator going to 0, blah, blah, blah. Then what do? Take the differential of each of them. That's the derivative in their language. So that's what he said in his textbook. He gave two examples in his textbook, and they're kind of interesting. The example on the left, using the old notation back from his days, written this way, ended up being, in modern notation, we would recognize this as the limit as x approaches a of radical 2a cubed x minus x to the fourth minus a times the cube root of a squared times x over a minus the fourth root of ax cubed. Clearly something made up to demonstrate a rule. Okay, so that's the first example he gave. The second example, a little bit easier. Back in their days, instead of writing a squared, they would write AA. It's kind of weird. But today, of course, that would be a squared over a. So this one is the simpler example, but actually shows up later in the book. And you can see this very quickly. It goes to 0 over 0. Applying the rule, we would get the right limit. This one's a little bit more complicated. Right? So the last time I taught, many years ago when I taught 161, I wanted to put this on the final exam. And the person I was teaching with said no. And I explained to him, but that's L'Hopital's example. And he said no. So anyway, try this on your own. It's really not too difficult. It looks kind of crazy, but it really is not too bad. If you rewrite these as powers, and then remember a is a constant, it's really, really not as hard as it initially seems. The second one is obviously pretty easy. So anyway, the L'Hopital's rule really should be called Bernoulli's rule. But because of their agreement, today we say L'Hopital's rule. That does not mean L'Hopital stole everything. He discovered a lot of very useful things for mathematics and physics. And he was actually quite significant in many parts of calculus from his own discovery, his own work. Okay? All right, that's it. See you Friday.